Hi, this is Kyle, and I'm here to talk about homework 2 for transport 2. Alright, the situation we have is that we have a capillary that has H2O water and D2O heavy water in a capillary, and we have even volumes of each amount. And I'm going to say for this problem, I'm going to say the positive z direction is to the right. So the first thing we want to find is overall mass flux n. And overall mass flux is equal to the total mass concentration multiplied by the mass average velocity. So we need to first solve for the total mass concentration and then the mass average velocity. So the total mass concentration is equal to the mass concentration of both parts added together. So to find the mass concentration of a component, you take the density of the component multiplied by the volume of that component over the total volume. And since both of the volumes are the same for each component, the volume of the component is actually just half of the total volume. So to find the total, we take our density of water multiplied by 1/2 total volume over total volume, and we take our density of heavy water multiplied by 1/2 of the total volume over the total volume. So this ends up, the total volumes cancel, so it's not dependent on that. And then the total mass concentration ends up being 1,055 kilograms per cubic meter. And if you want to look at the individual components, the water ended up being 500 kilograms per cubic meter, and D2O ended up being 555 kilograms per cubic meter, and that will come in handy later. So now that we have the total mass concentration, our next step is to find the mass average velocity. Our first step in this, we should find the velocity of each component. And an equation that will come in handy is the molar diffusion flux is equal to the concentration of the component times the velocity of the component. And we are given the molar diffusion flux, and we can calculate the concentration. So first we'll start with water. I guess I'll say I first looked at the generic equation for concentration, for molar concentration, and that's equal to mass concentration over the molecular weight. And since we know mass concentration and we know molecular weight, we can solve for the concentration. So then to find the velocity of a component, you just plug in what you know and then solve for the velocity. So we have the velocity of H2O is equal to the given molar diffusion flux, and since H2O is diffusing to the right, that's going to be positive. So it's equal to the molar diffusion flux multiplied by the molecular weight in kilograms per mole over the mass concentration. And this ends up being 1.0008 times 10 to the negative 4th meters per second. And then you use the same equation for D2O, just with the numbers regarding that. So since D2O is diffusing to the left, it'll be the negative direction. So its molar diffusion flux is negative 2.78 multiplied by its molecular weight, which is 0.02 kilograms per mole, over its mass concentration of 555. And this number is very nearly the same, but it's negative 1.0018 times 10 to the negative 4th meters per second. And now that we have the velocity of each component, we can figure out the mass average velocity pretty easily. So the mass average velocity is equal to the sum of the mass fractions times the mass fraction of the component times the velocity of the component. So since we have two components, we can just expand this out to the mass fraction of H2O times the velocity of the component H2O plus the mass fraction of D2O times the velocity of D2O. And when we plug in all the numbers, the mass fractions is equal to the mass concentration of the component over the total mass concentration. Then we just solved for the velocity, of each of them. So you get the mass average velocity is equal to negative 5.27 times 10 to the negative 6 meters per second. And now that we have the total mass concentration and the mass average velocity, we can solve for the overall mass flux, which is what we were looking for initially, overall mass flux. And to do that, we just plug in what we know and multiply. So we know the mass concentration, total mass concentration is 1,055 kilograms per cubic meter, and the mass average velocity is negative 5.27 times 10 to the negative 6 meters per second. And we end up getting the overall mass flux is negative 5.56 times 10 to the negative third kilograms per meter squared per second. So the second question was to make an order of magnitude estimation of the driving force. So first, we can assume that this system is isothermal and isobaric, which allows Fick's law to apply. So with Fick's law, the molar diffusion flux is equal to the opposite of the concentration, and then times the driving force, which is this dx dz. And then we have this diffusion coefficient that we can, since both materials are liquids, we can know that this is approximately 10 to the negative 9th for liquids. So then we want to solve for driving force, since that's what we want to estimate. So when we solve for driving force, we get its driving force is equal to the opposite of molar diffusion flux over the concentration times the coefficient, which is again 10 to the negative 9th meters squared per second. So then the next step would be solving for the concentration, which I did over here to the right. And the concentration is equal to the mass concentration of each of the components over the molecular weight of that component and add it together. So when you plug in the numbers that we know all of these, so 500 over 0.018 plus 555 over 0.02, we end up getting the concentration is 55,528 moles per cubic meter. And now we know all the different parts of the equation we can plug in, and we end up getting the driving force is negative 5.01 times 10 to the 4th, just 1 over meters. So then if we're estimating the order of magnitude, we can see that it's times 10 to the 4th, so that's the magnitude of the driving force. And part 3 of this problem was to draw these graphs at the initial, so like 0.1 seconds, which is like immediately when diffusion starts, the intermediate, which is 60 seconds in, and the final, which is just when diffusion is over. So initially we have, and it's showing the, I don't know if the color's coming out well, but the blue is the water and the black is the D2O. So initially we have the water on the left, and its mass concentration over its whole capillary on the left half of the capillary is 1,000 kilograms per cubic meter, and then on the right we have the D2O, which is this is before any mixing, so it's all on the right, and it's got its own mass concentration, and I believe it was 1,110 kilograms per cubic meter. So then intermediate, about 60 seconds in, we can see that the water and the D2O will begin to mix, or have begun to mix, and it hasn't fully mixed, so there's still a higher mass concentration of water on the left of the capillary and a higher mass concentration of heavy water on the right. And then at infinity seconds, or after diffusion is over, we'll have an even mix, and the reason D2O has a higher mass concentration still, because it has a higher density, so when you do that calculation, it ends up being 555 kilograms per cubic meter, where water is 500. So that's why water is lower. Alright, and then we're going to go down to the molar concentration. So initially, molar concentration, they'll both be at the same value since we're in moles, not mass anymore. And it's the same thing where the molar concentration of the water is at its maximum on the left of the capillary, and then it drops down to 0 on the right. And then for the H2O, the molar concentration is at its max on the right end of the capillary and drops down to 0 on the left before any diffusion. And then intermediate, so about 60 seconds in, it'll be similar to the mass concentration graph, to where you can see that the two liquids have began mixing, but they're not evenly mixed yet. There's still a much higher molar concentration of water on the left and a much higher concentration of H2O on the right of the capillary. And then once diffusion is complete, the molar concentrations will be even throughout, so it will be fully diffused. And then the next set of graphs is the molar diffusion flux. So the molar diffusion flux was given to be 2.78 in the problem at the initial 0.1 seconds. So this is when diffusion is like first begun. So there's gonna be no diffusion for a good majority of the capillary, and then right in the middle, right when diffusion is started, it'll be a very steep jump to that max molar diffusion flux. So like I said, it'll be a very steep jump, and water is going to the right, which we named as the positive z direction. So that'll be up to the max of 2.78, and H2O is to the left, so that'll go down to the same value but negative, since it's going in the negative z direction. And then the same at the left end of the capillary. The right end of the capillary will have no diffusion as of yet, since it just began. And then in the intermediate, it'll have a much lesser slope, if you want to look at it like that, and that's because diffusion has already been going on for a little while. So that means we now have diffusion in a wider area of the capillary. So it's not just this little small portion, since we now have for example, water is getting over to this right end of the capillary, so there's going to be a diffusion of water continuing to go to the right. And the same thing, the H2O will have the same diffusion, just in the negative direction. And then finally, when both liquids are evenly mixed throughout the container, there will be no diffusion. And then this last graph is the overall mass flux, and this was what we calculated in part 1. So the overall mass flux is in the negative direction, which means that the mass of H2O diffusing is greater than the mass of H2O diffusing, and that makes sense because H2O is heavy water, so it has a higher molar mass than H2O. So it's kind of similar to these molar diffusion flux graphs, where in the initial, when diffusion first starts, it's going to be a very steep slope up to the maximum. So there's no flux in the far left side of the capillary, no flux in the far right side of the capillary, but right in the middle where the two liquids are beginning to mix, it's a steep curve up to the max mass flux. And then in the intermediate, so 60 seconds in, there's gonna be a overall mass flux in a wider range of the capillary, but it won't slope as quick up to its maximum value there, because there's less flux over where it's reaching out in the capillary, but it's still there where it was 0 over in the initial. And then finally, when it's when the liquids are fully mixed, there will be an overall mass flux of 0, and that's similar to the diffusion flux because it's fully mixed, so there's no more diffusion of the two liquids. They're fully mixed with each other.